Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem shortest path in directed acyclic graph. Given a directed acyclic graph, find the shortest path from the source. They've clearly stated that the source will always be zero to all the vertex. Okay, so basically, what does the problem state? Yeah, given a DAG. Now, what is a DAG? If you remember, it's a directed graph with no cycles. If I combine this, then you call it as a directed acyclic graph. That is the definition of it. So over here, you're given a graph. Now, do you see a subtle change from the graphs that we were doing till now? Yes, you do. So if you see 0 and 1, there's an edge, but we have added edge weights to it. We are saying the edge weight is 2. That means to go from 0 to 1, it will take you 2. To go from 1 to 2, it will take you 3. So in short, if I ask you to go from 0 to 1, what is the shortest path? It takes 2. Are there any other paths in the graph? The answer to that is no. So I can say, if I say node 1, the distance is 2 because that is what it will take. For node 0, the distance is 0. Why? 0 on itself because the source node has been clearly stated as 0. So 0 to itself will be 0, right? If I ask you for the second node, it states 3. Where's the second node? Here. How many paths are there? One is this, which takes 5. One is this, which takes 3. So thereby the shortest path is 3. So the question is very straightforward and simple. You're given a source and it will always be 0. From 0 to all other paths, like all of the nodes, 0, 1, 2, 3, and so on till n minus 1 node. You have to find me the shortest distance to travel. Shortest distance to it. That is what the question states. So we have learned toposort till now, right? So you'll be applying toposort, but the algorithm will be slightly different this time. Okay, I'll be combining toposort with some relaxation of edges to solve this. So I'll write the steps, and the process that I'll follow is first I'll tell you the algorithm, then we'll go and code it, so that after this process you have a very strong hold of what we are doing. Once you understand this, I will tell you the intuition. Okay, you might think, why not intuition at the start? Because if I tell you the intuition, you might understand, but in a very blunt manner, you'll understand. You won't understand in depth. But once you have the algorithm and the code in the brain, and then I tell the intuition, you'll be able to connect it and you'll be much like it'll be easier for you to absorb it. Okay, so this is the DAG, and this is the corresponding adjacency list. This time, carefully see, the 6 has an adjacency node of 4. So 6 has an adjacency of node of 4 with a weight of 2. So instead of storing an integer, previously it was like 6 has an adjacency node of 4 and 5, 4 and 5. This is what we were storing, right? This time we will store pairs 4, 2, 5, 3 because this is 5. We'll store pairs this time. This time it will be list of pairs. Either you are in C++, it will be vector of pairs. What you will store, if you are doing a Java, it will be array list of pairs that you will store in this particular thing. Remember the third lecture where I told you how to store graphs? If they have edge weights, you always declare it as pairs, and you store pairs where the first guy will be the adjacent node, the second guy will be the weight of that edge. Remember? So that is what I have done over here. So the question stated the source will always be 0, but we will try to solve this problem for any given source. So source can be anything. So thereby what I'll do is I'll say for this graph, assume the source to be 6. For this graph, assume the source to be 6 because I don't want you to be sticking with 0 because that will not help you out. So we can have any source because the interviewer might give you the question as stating as any source. So any source. Okay. So what is the step 1? So the step 1 of the algorithm is very simple. Do a toposort. Do a toposort on the graph. Yes. Do a toposort on the graph. Now, how many ways do you know to do a toposort? There are 2 ways. One is the DFS way. One is the BFS way. Do whichever you wish to. I just want the toposort for this particular DAG, which is the directed acyclic graph. So let's quickly do the toposort for this DAG. So I'll be using the DFS method to find the toposort. So you know the DFS method is very simple. we always take a stack data structure which stores the toposort. Whenever we complete the DFS for a given node, we put it into the stack. We take a visited node, that is what we take, and we always run something like this for I equal to 0, and we go until 6, and we say if not visited of I, then please call the DFS for I. If you remember, this is always done for the components, right? So what's the first value of I? That's 0. So we'll go and call the DFS for 0. The DFS of 0 is called. Whenever the DFS of 0 is called, please make sure it is marked as visited. Now, who are 0's adjacent nodes? It appears that 0's adjacent node is 1. So go and call the DFS for 1. Perfect. So again, mark it as visited. Who are 1's adjacent node? Appears to be 3. So go and call for 3. So I called it for 3. Who are for 3? Appears that there is no one for 3. Mark 3 as visited. And it appears that for 3 there is no one. So what I can say is for 3, the DFS call is over. And whenever the DFS call is over in toposort, if you remember, we just took that 3 and put it into the stack. Go back. 1. Do we have any further adjacent nodes? No. Put it into the stack. Go back. 0. Do we have any further adjacent nodes? No. Put it into the stack and go back. So what I can say is this particular DFS call is done. Let's increase the value of I. 1. It's already visited. 2. Not visited. Call it for 2. Mark it as visited. For 2, do we have any adjacent nodes? Yes. What is it? 3. But it's already visited. No further DFS calls. So 2 is also done. Go back. So once you go back, this is done. Increase the value of I. So this will be 3. Will we do a DFS call for 3? No. It's already visited. Increase the value 4. So will we do it for 4? Yes, we will do it for 4. Mark 4 as visited. After that, look at 4. It has 0, which is visited. You see 0 is visited. It is. And it has 2, which is also visited. 0 and 2 both are visited. Separately, no further DFS calls. So it will go back and the DFS, put it into the stack and go back. Next, it's 5. For 5, mark it as visited. And 5 has adjacent node as 4, which is already visited. So no further DFS calls. Please make sure put 5 into the adjacent nodes and go back. Next, into the stack rather. It'll be 6. Similarly, it will happen for 6. Mark it as visited. And you'll find that for 6, we have 4 and 5 as the adjacent node. 4 and 5 both are visited. So no further DFS calls. Put it into the stack and go back. So apparently, once this for loop has been completed, all the DFS calls have been completed, this stack will store the toposort. Now, if I quickly erase this off, let's quickly erase this off. So the step 1, I can say, has been completed. And the toposort is very simple. It is 6, 5, 4, 2, 0, 1, 3. And if you carefully see, there is an edge between 0 to 1. So 0 appears before 1. There is an edge between 2 to 3. The 2 appears before 3. So this is indeed a valid toposort. I can easily say that. Now what is step 2? Step 2 is very, very simple. You take out all the nodes from the stack one by one. Take the nodes out of the stack one by one. Nodes out of stack. And relax the edges. You'll hear this term a lot going forward, and relax the edges. Okay, this is the step 2. So in order to relax the edges, we need to declare a distance array, and that should be marked with infinity. Let's do it. The distance array has been declared, and what you'll do initially is just make sure everything is marked as infinity. Now let's start relaxation of the edges. But before that, please make sure whatever is your source node, just go to that source node and make it 0. Just make sure that you go to that source node and say that, hey, I know one thing. If you start from 6 and if you end at 6, the distance that you will take will always be 0. So make sure you do that, okay? Next, whatever is on the stack stop, this is stack stop. Stack is always last in, first stop. So the last in was 6. So this is stack stop. So make sure you take it out. So node equal to 6 has been taken out. Now, whenever you are at 6, you know the distance to 6 is 0. How did you figure this out? Because that is what it was stored over here, right? Now figure out the adjacent nodes of 6. The adjacent nodes of 6 is 4 and 5. The adjacent node of 6 is 4 and 5. So try to go there. So you'll be like, okay, I'll try to go to node 5. I'll also try to go to node 4. Okay, these are the 2 nodes that I'll try to go to. These are the 2 nodes that I'll try to go to. Now, have a careful observation. have a very careful observation on this graph. In order to go from 6 to 5, which is this, what is the edge weight that is required? 3. Do you see? 3. So you say, if I go, I'll require a 3. So can I say, if in order to reach 6, I require a distance of 0, from 6 to 5, I require a distance of plus 3. Can I say the overall distance will be 3? Because from 6 to 6, it was 0, and from 6 to 5, it is 3. So the overall distance will be 3. And you see, to node 5, it was infinity, right? And if you see, we are reaching a distance 3, which is better. 3, obviously. So you go and update this to 3. You go and update this to 3. Don't do anything else, just go and update. Similarly, see over here, to node 4, what will you require? 2. So please do a plus 2. The distance will be 2. Similarly, go to node 4 and say, you will require a distance of 2. You will require a distance of 2. Done. Once you have checked out all the nodes, complete it. Next, get the next node out, which is 5. And let's see what is the distance taken to 5. That states me that the distance has been taken as 3. It clearly states as 3. The distance is 3. What does it mean? Whatever was the source node, in order to get to node 5, I required a distance of 3. That is the meaning of it. So for node 5, look at the nodes. So the nearby node is 4. So the nearby node is 4. How much will it take if it goes from 5 to 4? 1. Plus 1 is what it will take. Let's take the distance. So previously it took 3 in order to reach from 6 to 5. That's taking plus 1. The total distance will be 4. 3 plus 1 is 4. And if you carefully see, in order to reach node 4, I already have a better option. I already have a better option of 2. So will I take this 4? No. Why? Very simple. Because from 6 to 5 and 5 to 4, it will be 4. And from 6 to 4, it will just be 2, which we already have taken. So nothing to be done. Omit this off. Next, take the next guy, node 4. At the moment you take node 4, what happens? You again check for the adjacent nodes. That's 0 and 2. So one is node 0 and the other one is node 2. This takes a distance of plus 3. This takes a distance of plus 1. Very simple to figure out. You have already stored it. So plus 3 and plus 1. Previously, how much distance node 4 took? 2. Again, very simple to get from here. So 6 to 4 took a 2 plus 3. So till node 0, what will be the distance? It will be nothing but, very simple, 5. And till here, it will be nothing but 3. Why? 2 plus 3 will be 5. 2 plus 1 will be 3. So node 0 states it's infinity. So you update it to distance 5. And node 2 says it's infinity. So you update it to distance 3. Done. So once you've done this, omit this as well. Simple. Next, take the next node, which is 2. So node 2, what is the distance taken? 3 from the distance array. So from 6 to 2, you know the distance is 3. You know the distance is 3. From 6 to 2, you know the distance is 3, and that's very obvious because it took this path. It took this path, right? So from node 2, where can you go? Let's quickly check it out. From node 2, you can go to 3. So let's write it. You can go to 3. And if I go to 3, I will require how much? 3. I'll require nothing but 3. So I'll just add a 3, and that will give me nothing but distance of 6. So till node 3, I get a better option than infinity. So I take it. Next, erase it. Let's quickly take the next one, which is 0. So node is 0. The distance taken is 5. From 0, you can go to node 1. And the distance will be plus 2 of it. So the distance will be 7. What you can do is, you can say 1 to be 7. Very obvious, because if this was taking 5 and this takes another 2, so 5 plus 2 will be 7, which is better than infinity. So done. Omit this. Let's say the next guy, who is 1. So from node 1, what is the distance? 7. You see, node 1 has distance 7. Where can 1 go? 1 can go to node 3. How did you get this? From here. What is the distance? Plus 1. So what will be the distance if I go to node 3? 8. Will I take this? No. Why? Because we already have a 6. So omit this. We will not take it. Similarly, we'll get the next guy, which is 3. So node is 3. So from 3, where can you go? You can go nowhere. So nothing to be done. Omit this. This is the step 2. So once you have done the step 2, you can see that the distance array actually stores all the shortest distance from the source 6, and the topo sort is empty, and we have figured out this is our answer. Yes, this is what our answer is. So I hope you have understood the algorithm. It's very straightforward and simple. Figure out the topo sort. Once you've done that, take one node out and just keep on updating the distance array. Keep on updating the distance array every time. Once you're done with this is your particular answer. What's the intuition? After the code, I'll tell you. So I hope you've understood the entire algorithm. Now it's time to code it up. So I'll be coding the C++ solution on the right, and you can figure out the exact similar Java code on the left. So as you can see, we are given the number of nodes, the number of edges, and all the edges data have been given over here. The edges data is like U and V and the weight. So the first step is definitely to create a graph. So let's quickly create the graph, which will be something like vector of pair. We need to store pairs this time, so adjacency of n. Okay. Next, we go across and say I and I equal to 0, I lesser than n, I plus plus. This is something which we will do. Now the next thing that I'll do, we'll say adjacency of u. By the way, just to make your understanding better, edges of I 0, because every index has a vector, and the vector resembles 3 guys. That is the meaning of this. So u is this, v is edges of I of 1, and wd is on the second index. Simple as that. Next, I say adjacency of u. Can you please store the adjacent guy, which is v, and the weight is wt as a pair? Stored. Next, you always find the topo. So that's the first thing. So what do I need? I need a visited array. I need a stack. And do I need anything else? No. So let's quickly create the visited array. So I create a visited array, something like this, which is capital N equal to 0. Perfect. I need a stack. So let's quickly create a stack as well. Perfect. Next, I need to figure out for all components. So let's go for all components. And we say if not visited of I, we go across and say, okay, listen, go for the topo sort. And in the topo sort, what do we need? We need the node, we need the adjacency, we need the visited, and we need the stack. So this is what I'll do. I'll get my topo sort. So now quickly write the topo sort, and that's for DFS. You can always write whatever you wish. You can do the BFS as well. Void DFS, IND node, and I'll say vector of pair of IND adjacent. This is how the graph will be. Perfect. Next, I need the visited. So let's see the visited. And this is the stack, which is INT, and please pass it using reference. So that's what I will do. What's the first step of DFS? You say, by the way, this will not be DFS, this will be topo sort. That's what we are naming it. Visited of node will be 1. And while going back, just make sure you push on the node. Next, I traverse for all the adjacent nodes, which is adjacency of node. Now I know V is the node is right at the first, because we are storing pairs. So I say if not visited of V, please go and call the topo sort. That's very simple, because we will be calling the topo sort for V, adjacency, visited, and stack. Done. So this is how I'll call the topo sort. So I can say once I've done this, the stack is ready and it has all the topo sort elements. Next, step 2, do the distance thing. Do the distance thing. And what do I need? For doing the distance thing? I need a vector which stores all the distance. Perfect. Please make sure everything is initially marked as infinity. So I this, and you can go on like I less than n, I plus plus, and you can go as distance of I equal to infinity. You can call it as int max. Super simple. Next, you have a source node, and that's always 0. If the question does not mention your source node and it gives you have to write distance of src equal to 0. Next, you start from while and you say stack not empty. That's the first thing you'll do. What will you do over here? You'll say, okay, let's get the node, which is stack.top. And let's do a stack.pop. Perfect. Next, you need all the adjacent nodes. So please go across all the adjacent nodes. And over here, id.first stores the adjacent nodes. and id dot second stores the weight, and I need to relax it. So distance of node is what it takes to reach the node, and from u to v it takes weight. And if it is lesser than the previous way of reaching v, it can be infinite, it can be anything. If node plus weight is lesser than the previous way of reaching it, I do not do anything. I just go across and update it to the new node. This is what I'll do. I'll just update it to new node. Once I've done this, I'll return the distance. So this is how simple it is. And after this, I'll go across and run this and see if it is fine. It gives me a compilation error because I think my bad, it'll be pushed back. So let's quickly run this. So I've done a slight typo. Over here, it will be M because number of edges. I'll quickly compile and see if it is giving us the correct answer. In compilation, we see that it is giving us the correct answer. Will we submit? No. Let's wait. Let's read a couple of statements. So it says find the shortest path, but does it mentions about what if we do not reach? So it doesn't mentions about it. I'll ask the problem setter to add it up. But as of now, there's a trick. I'll go here and I say, okay, they're expecting if it is 1e9 to see out infinity, not reachable. So they're expecting 1e9 instead of int max. So I'll just assign 1e9 because what they're expecting is if it's not reachable, it should be 1e9. So I just did a slight hack. I just checked in, but I'll ask the problem setter to update the problem statement. Don't worry about that. I'll now quickly run this off and see if it is running fine. Okay, it is. So all of these test cases to pass. So we have understood the algorithm. We have understood the code. Now let's discuss the time complexity. Then we'll go across to the intuition. What are the time complexity? A topo sort, plain DFS, whatever time the DFS takes. What about this? The number of nodes is what the stack will always give you. That's for sure. The number of nodes is what the stack will give you, which is n, into all the neighbors. Into all the neighbors. So if I ask you, in total, this for loop will run for how many times? Let's go back. So can I say, in the iPad, runs for first run 0 will run for once, twice, thrice, 4 times, 5 times, 6 times, 7 times, 8 times. Can I say the internal for loop for the adjacent nodes will run for 1, 2, 3, 4, 5, 6, 7, 8 times, which is nothing but 1, 2, 3, 4, 5, 6, 7, 8, which is nothing but the m edges. And I say overall it will run for m edges. So n plus m is what the second loop will run. This is a plain DFS. This is plain DFS n plus e, the number of edges, which is m. But this is very obvious, right? Because the stack will give you n, and in total the adjacent nodes is nothing but the number of edges only. So we have understood the time complexity as well. Now it's the main thing about. Okay, so you've understood everything. Now you must be thinking about the intuition. Why topo sort? Why not some standard algorithm? Like in the next half of the lecture, like in the next half of the series, we'll learn algorithms like Dijkstra and a lot more, which helps us to find the shortest path. Will those algorithms work? Those algorithms will definitely work. But why did we do a topo sort? Let's understand. So what was the topo sort for this? If I write it, it was 6, 5, 4, 2, 0, 1, 3. Something I know for sure is there is no one before 6. There's no one before 6. So something I know for sure is the initial guy is 6. So I took the initial guy to be 6. And 6 took me to 4 and 5. So apparently, once I started from 6, which was the topo sort, then I could go to the next guys, and that will always be in my topo sort only. Because topo sort starts with the first guy who has no one into it, and then takes to the next guys who he was into just. So it takes it to 5 because it was just to 5. And 5 says, I'll take you to 4. Got it? So what topo sort did was, it stated as the first guy, I don't have anything. I'll start off from myself. And since I was the source node, I'll assign myself to be 0. I'll go to 5. I'll figure out the answer for 5. Then I'll go to 4, figure out the answer for 4. Then I'll go to 0 and 2, figure out the answer for them. Then I'll go to 3. Then I'll go to 1 and I'll figure out. So what I did was, I moved sequentially. The nodes which are reachable first, I moved them. Then this, then this, then this, then this, then this, then this. I moved according to reachability. So what happened was, I minimized the number of steps. to big O of n plus m, which is much, much better than any standard algorithm because Dexter takes more than this. The only reason it works is because we are making sure there was no one before 6 and we computed for 6, then we did for 5. So when we are doing for 4, we know all the previous guys have been computed and I can only reach 4 via 6 or 5 because it is a directed graph. 2, 0, 1, 3 cannot make me reach 4. The guys who can make me reach 4 are 6 and 5 and they have their answers computed. So I'll compute now 4. Now for 2, these 3 guys can make me reach 2. So these answers are computed. So I started with a very small and then I expanded it to 2. Then I expanded it to 3 and so on. That is how we will do it. So in short, the intuition is very straightforward. If I'm reaching a node, I know all the previous nodes have their answers, right? So that was the simple intuition. We still have a problem. I'll leave a Stack Overflow link on the description. You can check it out. The answer is given over there. You can read it again and again. But I think it is more or less clear to you now. So I hope you have understood the algorithm, the code, and the intuition. So just in case you did, please make sure you like this video. And if you're new to our channel, hit that subscribe button right away. Please do consider subscribing to us. If you haven't checked out our DP series and the SG sheet, the links will be in the description. And yeah, with this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken